It goes up 1 every 10 ticks.
Okay, Corey, I'm gonna start the stream now.
Okay.
Hello, everyone. Welcome to TUNG Tuesday number 10. I'm joined by Corey.
As always.
Corey. Oh, wait, no. Let me
Yes.
check if the live stream is up. Yep, it is up. Okay, so this TUNG Tuesday, we made a Fibonacci program this time. So now we get to run it. Hey, JJPRS306 is here.
Who's
Hello.
that? Oh yeah, that's Lawrence. I almost forgot.
Oh, Eddie won't stick for too long. Okay.
Ah.
Not good. There, okay. Let's turn this up to like 300. Hey, David, can you tell Corey to work on the crystal crab? What is that?
He cannot.
Okay, well.
Okay, that's
Oof.
2
Gigantic lag spike.
delays.
Okay. 40.
Okay, so 1 tick,
Okay.
2 tick, 3 tick, 4 tick, 5
Oh,
ticks,
yeah, if anyone's wondering, Corey's working on a
6
stopwatch.
ticks,
Oh,
7 ticks,
okay, let me look
8
here.
ticks. Actually, how many ticks does reset take?
Does reset take?
1 tick,
Yeah, because
I
all it's
think.
doing is just going into that one inverter there on the JK flip-flop.
But there's a blotter going into the inverter.
Is a
So
block?
would that be 2 ticks?
Yeah, that's 2 ticks. Then.
Okay. In theory, this works.
In theory, this works. Oh, I didn't mean to do a clock step.
Okay, let's test it, I guess. Let's test it at 10 ticks per second. Wait, that would be way too slow.
Yes, very slow Fibonacci. This is still at 300 ticks. On the fastest clock speed.
Okay, I think it works.
It works?
I have to look at it at a slower tick rate, like 25.
Oh, yes. We cannot wait for that. Carmen has to show up. Like, she probably has no homework. Or anything to do.
I'll text her, I guess.
Yes. I already told the Tongue Discord that I'm streaming, so hopefully Jimmy sees that. 13 is a Fibonacci number. Jimmy Cushion. I think his last name is spelled differently, but yeah, that's basically it. Yeah, Kushi, I think. Let me look on the Discord.
Is it IE or...
I think it's
Oh, it's
Kushni.
Y.
I don't really know.
Yeah, it's Kushni,
I'm just
I
saying.
think.
Okay, so I'm going to share my progress this week to the uninitiated. So, I finished the computer. I made it blue. I made this cancerous wiring. I finished the control unit, which is lots of cancerous wiring. It's very meticulous cancerous wiring. And then, I fixed the stack, so it now looks like a normal stack, which is great.
Okay, it's skipping 99, so that's not good.
Yeah, you have to probably time it. You have to probably make it wait
Oh,
later.
I know, it has to be 99. It can't be from 98.
99. The 99 pulse will be shorter though.
It won't be. Because this should exactly reset just before it reaches 99, so I have to add the 99 thing, so like exactly reset just before 100.
Okay. Let me actually check. So we're at this memory address. So the next memory address should be pretty straightforward then.
Okay, in theory this works. Also, it's going to be really slow.
I have to open Google Docs and look at the computer docs so I can get some reference. Oh yes, I will I have to make a video, like a programming guide to this computer. That would be good to make. Come buy my stopwatch. It's about the size of a garage. Well, we don't know exactly how big each unit is. Like each square unit. I don't know, it might be an inch. If so, then this computer is not that big in height. But I don't know. Okay, so let me look here. I want to make it so at the end of the jump, at the end of when it halts, I want to be able to unhalt, and then it starts drawing something to the screen. A line with slope of 1. That's a good thing. So let me look at my program. Jump if not, okay. Oh. I do have the program. Okay. Well, let's see if it works. 3,000 ticks per second it is. Oh, how much computing power? Okay. It has a 10 hertz clock. It can do one instruction per cycle. I mean, one instruction per, on average, I'd say on average, I'd say like 4 cycles. So, you can do around like two instructions a second. You can have 256 output devices. You can have 256 input devices. Here's what the port looks like. Where this is data, this is control lines, this is computer ready signal, this is IO ready signal. Why am I lagging? Stop it, halt it, please. I halted it. Okay, well, your messages show up. You're watching me do something that I did maybe 30 seconds ago because there's lots of delay, so. Okay, well, I halted it anyway. Time to lag you some more.
It's at 99.
More lag.
Good. David, it works exactly like it's supposed to. I think.
Oh, good. No, it is not good by today's standards. Today's standards are like impossible to do in Tongue. Hopefully I don't break the screen. It's kind of weird what it's... Oh. It just broke all the memory cells. Well, that's great.
Yay. Now you're going to have to touch the button you told us.
Yes, more lag for Eddie.
You touch the memory reset button.
The memory reset button. Bad
Yeah.
things. It resets the memory.
But didn't you break the
Hey,
memory?
Carmen's here, Corey. Carmen, Jimmy isn't here yet, but he's coming, so just wait.
Didn't you break the memory though?
No, I mean, I broke the screen memory.
Oh, okay, that's good. You
You can...
can clear that. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3.
I wonder what's happening. Okay. Well, let's look at the program.
Okay, there's a problem. This clock does double the amount of delay that it's supposed to.
What is it, a delayer clock?
No, it's a blotter clock.
Oh. Why do you make a blotter clock? Isn't that, like, really fast? And for you to do a blotter clock, you need to have...
No, I have 9 blotters and an inverter.
Okay, so that's a 10 inverter clock. I mean, that's a... Yeah, it's a 10 inverter clock. So what you need to do is you need to make a
A
5 in...
5 inverter clock.
Yeah, 5 in... You need to make a 5 inverter monostable. So you get an even time. So, like, it's on for half the time, off for half the time.
How do I do that?
I can show you. Let me show my screen.
Um, Wait.
You're seeing my screen now, right?
Yeah.
Is it laggy?
Yeah, pretty laggy.
Oh, okay, whatever.
Wait, does this do the trick? Or no? Does that make it random?
Putting a button?
No, not that. Wait. I need to... That up to there. Is this random? Or is it controlled?
That is not random.
Okay,
But the way I
that's
would...
good, right?
way I would do it is I would put this... But yours doesn't really matter. Doesn't really matter if
Okay,
it's inverted or not.
let's check if it works. Whoa. Whoa, that's not good.
What's happening?
Bad stuff.
Oh.
They're flashing on and off way too quickly.
Did it break?
No? I mean, maybe. Most likely.
If I were you, I would make just a 2 delayer clock and make a 1 delayer monostable. That's the same clock I used for the computer. Its speed doesn't really matter for the clock either, Corey. I would just pick one that's stable. Like this.
Okay, this is way too fast.
Yeah, just do a 1 delayer monostable. Okay, let's look at the program, I guess, now. Okay. This is the end of the Fibonacci program right here, where your number that you select for n number of Fibonacci numbers goes to 0. And then you have to halt. And then the user can unhalt. And then what we do is we assign A to be 0, we assign B to be 0. So we're just setting A register to 0, B register to 0. We're moving that into the F register. We're outputting the F register on IO port 2. Then we're sending the control signal IO 11010000, which is, if I'm correct, write, data, and read. And then we move F to A. So we move the value of f into a, and we assign b to be this, which will add 1 to both the x and y coordinates of the input. Well, f is 0 because we made it that, and then we're moving that into a. We're assigning b to be this. This is the thing we add to it to increase the slope and the x and y, and then we jump, if not overflow, to line 38. So line 38 is this one, I think. Yeah, so 2, 4, so 6. And then 32, yeah. Okay, this is 38. This is where we want to jump back to. So this is a continuous loop until it overflows, which basically just means, like, the computer... It's like calculator overflow, basically. That's how I'm just going to say it. Oh, Jimmy is here. Okay, Jimmy, I have to show you something. Okay, Jimmy, I already showed everyone else in the last 5 minutes, but I'm going to show you. I wrote a Fibonacci program. It's the one that I sent you in Discord, and I implemented it with the computer, and it works. Also, I made the computer blue because we need pretty colors, apparently. Okay, so we have Corey's very improved BCD display thing hooked up to the computer on IO port 1, and this is just a comparison between the two. So it used to be all horizontal, now it's stacking vertically. Okay. Let me start the computer. So clock speed 1 is just the first clock speed. Now it's halting and it's waiting for user input. Oh boy, lag. This light indicates that the computer is waiting for the
David,
user. What?
if I just kill the 7th bit too, does that mean this counts up by 2 if I, like, move these by 1?
What do you mean it counts up by 2?
Okay, so instead of making this bit not useful, we make this bit not used, so there are only 6 bits, but we imagine there's a 0 here, so it counts it by 2 instead of 1.
Maybe? I don't know. Let me just show Jimmy this first.
Okay.
Okay, so this is we put in our n numbers of Fibonacci number here, so this will count up to n numbers of Fibonacci. Actually, let me stop sharing my screen so we can get better FPS. Okay, so we put in our number here. Computer is waiting for us. We press this button, which tells the computer to stop halting. And okay, yeah, we just pressed it. 1, 2, 3, 5, 8, 13, 21, 34. Oh, bad visual glitches. 55, 81, 144, and 233. There we go. Why are these visual glitches? Okay, bad. Good. And, okay, yeah. That's basically it. I can show you inside the computer when it's doing stuff, but that might kill my game. I can try it. We can toggle halting, but in programs like this way. It's user halt, basically. That resets all this reset just resets all registers. Yeah, I should show you this control panel. Okay, so I built this for debugging and other things. So we have we have a display of all the main registers here.
Okay, David.
Yeah, what?
This lever was only hooked up to that thing, right?
What?
This lever, because I accidentally deleted it.
Yeah, it was only hooked up to that. That's just
Okay,
that's
good.
just to enable the yeah, okay. It's fine if you curse, I don't really care. Only if Jason does it. Okay. So
That's Jasonist.
I'm not discriminating. Okay.
Are you sure?
Yeah, I'm not. Oh boy. Lag spikes, though. Okay, so we have all the display of registers. We can put a value onto the bus, like this. This bus input is inverted. I just never changed it, because I was just lazy. So this is really 1 if I want to go put it into the A register, so I can... No, I'm not going to kick him off the Minecraft server. Okay, so...
Who?
JJPRS306 said someone kick him off the Minecraft server.
Which Minecraft server?
This one.
Our school?
Yes. Our school's name initials are CMS, which is Christian Minecraft server, even though that's not what they intended.
It
Okay.
is what they intended.
Okay, yeah, whatever. Okay, so let me just get rid of that. And we can set ALU output register, which is this one. And you can set the flag register, which is this one down here. Here's the stack pointer, so this is like the top of the stack of the memory address. And then current CPU cycles, there are 8 here. Here's the clock pulse, here's if it's idle, if it's running. Here's the memory data register, here's the memory address register. Here's the input IO address register. Here is the memory data bus, so that's this thing. The thing that goes into the memory and goes through all of it. Here's the output IO address register. So for each IO devices, they each have an address register. So there are only 4 ports on the main computer, but you can expand it up to 256 with these ports, and it's really easy to expand because you just need to connect up these wires that are just facing each other. And the best part about this is that you don't have to actually hard code it to be a specific address. You just push these levers, so it becomes, this is like IO port 1, but we can just change it to become IO port 0 or anything else we want. So yeah, so that's for both of them. And then IO data in register. So here's like the input register from one of the input devices. Here's the IO control register. Okay, so the IO control register is for these control lines. These are just for like controlling an IO device, like making it like write. Like here, I have it hooked up to this display, like write, clear, data, read, like all those things. And that's just for like a specific IO device thing. Okay, and we also have register, select register. Now for the move command in our computer, basically, we have to select a register we want to move. So with the move command, it's 2 bytes. The first byte is the opcode plus the register we're moving from, the source register. And move is a confusing word. It's really just like copying a value. It's not like erasing the value in the source register. And what I have to do here really is I take in memory it's 2 bytes, and the second byte is okay, I thought Jimmy was leaving, but he's not. Oh, wow. This is not connected. How did I not catch that? Oh. Well, it doesn't really matter. I didn't have to use it, but that was bad. Okay. At least my Fibonacci still works. Okay, so what I have to do is I have to take that register like address, and I have to put it into this register, which I then decode it using a non-bad decoder. So it's a better decoder.
What?
101 will not be mad. This is a perfectly timed decoder, so literally no other values will turn on. I perfectly timed it with these blotters and inverters, and there's no delay between any of the inputs, so that's good. And then this is then bused over to the registers here, which I then connected with really sloppy wire over to the set lines for all the registers, and I can move values and stuff. And the selected register, this is just a display of these connected up to there. Oh, I never connected this up. Okay, time to do that now.
David, good job.
Wow, that actually made it. Okay, whatever. I will connect these up, and we'll get more lights, which equals more lag, but it's fine. Lights lag your game so much. Also, when I look in this computer when it's doing its program, it like kills my computer. Oh yes, Jimmy, my science teacher said he wants to do Logic World after he saw this, so like in his class, he wants to use it, but he wants to use the mobile version. So we should hook him up probably. Okay, well, that works. And these lines are also connected up. This is like the set for this too. So, oh yes, here's the really bad programming interface. So basically, you put in the address you want your instruction to be. You put in the instruction here, and this is bad because you have to memorize the instruction, and then you press write, and then you can check from this address by pressing read, and it'll read out over to here on the memory data bus so you can see what's in it. Yeah, I know, I gave him your email address. I sent it to him. Hopefully he responds. This is a very dangerous button. Basically what this does, it erases memory. And this is dangerous because I spent many hours putting the program in, which just shows how bad this interface is. But whatever. If I press this, what will happen is it'll start this binary counter, which then the output of this goes into the address lines for the memory. And okay, it starts this clock here. It comes in from, like, when you press erase, it starts this clock, which then starts going, and then the output of this clock goes to the right line for the memory. Ooh, more lag. And also, what happens is, let me look here. Okay, it goes, and then once it detects that it's at the end, so like all ones, it then goes into this T flip-flop, and then this then stops the clock, and it stops, and then this T flip-flop resets too. It's very satisfying. You should have a lock on the erase memory so you don't have to switch flip. You don't have a switch flipped to press it. Well, I have this done thing to like tell the user that it's not done doing the memory, but probably locking this button is a much better idea. Yeah. I'm not gonna fiddle with it now because if I screw up, it's like the end of this. I'll just do it later when I feel risky. Okay. Right now I want to be able to draw a line to this display. So like maybe like you give slope and y-intercept information to this. That'd be cool. And then what would be cool is if I could maybe load in Wild Javari's 64 by 128 display, but it'll probably crash my game just considering how much stuff I have in it already. But that would be really cool because then I could draw really big lines, because this is only 16 by 16. Oh yeah, Corey's making a stopwatch now. Corey, how's the stopwatch going?
I just found out that the speed for 100 ticks per second is actually too slow, and it actually has to be like 1,000 ticks per second.
1,000 ticks per second. That's fine. I run my computer usually at 1,000.
Except it's actually not very accurate.
Oh yeah, I should actually tell Jimmy There are two clock speeds to this computer. One is a 1 delayer clock speed. One is a 2 delayer clock speed. The 2 delayer clock speed, I don't know. I included this when like tick speed wasn't you couldn't like modulate it, but now you can, so it really doesn't make any sense. Didi, I'm not going to Discord you while I'm doing the stream right now. I have to be doing the stream. Oh yeah. Now that I finished this computer, I'm going to be doing the 50 by 50 by 50 challenge issued by Cody McNormy and is proud of it. I think that's how you say his name, or I don't know. I'm going to be doing that challenge, so I've learned lots from this computer, so I think I can make it smaller. Okay. Let's take a poll. Jimmy, you've seen my program, right? So I might as well just tell you the programming language of this so you can get an idea for it. Oh no. I want that to be there and this to be there. Okay, good. Okay, so oh yeah, this demo program, it's Fibonacci and stuff. I'm just going to be telling you this. So here are the instructions. What I'm doing is I'm making a document that will show all of the... Oh, okay. What I'm going to be doing is I'm going to be making a document that's like that can show you all of the specs of the computer and the programming language and all that other stuff. But I'm just going to show the people on my stream right now and what it is. So one command is store. This will store register value into memory address. Load. Oh yeah, some of these might be wrong. This is the thing. Yeah, like that. That shouldn't be there. Some of these things are wrong, so I'll just correct them as I go. So load will load this is weirdly formatted, but I have to do it this way. So I will load a memory address into a register. So value in memory into a register. Move will move register from source register to destination register. Add. So the weird thing about this computer is I didn't really plan out the instruction set that well, so I just had to go with it. But add is its like own command where it'll add A and B and store it in the output register and set the flags register too. I did this because I think I made the opcodes too big. Well, I just have way too many instructions. I think that's just it. What I should have done is I should have just made a command called ALU, and then that's followed by a like 4-bit opcode that will do any of these, basically. I should have done that so I could fit it all in one command and then make this much more simple, but I did it this way anyway. I don't know why, but whatever. So add will add A and B, subtract will subtract A and B, rotate left, A register will rotate... What? No. This is supposed to be left. We'll rotate left the A register, rotate right will rotate right the A register, rotate left B will rotate left the B register, rotate right B will rotate right the B register, increment the value of A plus B registers. So it'll increment A plus B, we'll just add 1. This will decrement the value of A minus B. If you want to this will only decrement A if you put it in, so you can't just put in B by itself, or else bad things will happen, because for decrement, all I'm doing is I'm turning on negate B, so if you turn on B, it'll just invert B. So it can double as an inverting thing, but it's just weird stuff. So XOR, that'll XOR A and B, and will AND A and B. Not will negate A and B. Or will OR A and B. Push. Now, this computer has a stack, which... I don't know. I just thought it was necessary because it makes programs way smaller and easier to understand. But what happens is, in a stack, you push things and you pop things from the stack. So it's last in, first out, basically.
David,
What?
when you place down an inverter with 0 ticks, it looks like this.
Corey, I think you have to set your
Yeah.
microphone to the Logitech ones.
Oh,
Yeah.
okay. I will do that.
Okay,
Oh, it's much better.
that's
Before,
good.
before it was like borderline ear rape.
Okay.
Okay, now it's fine. Okay. So we can push registers to the stack. We can pop off values from the stack to a register. Halt will pause the computer. This is a toggling thing. So if you well, the computer can't really toggle once it's in halt, but the user can press toggle halt, which will toggle halt on or off. In will take value from register and it'll take value from IO port from an IO device and put it into a register. Out will take value from register and put it into an IO device. And both of these use handshaking, so the computer will ask the IO device like, "Are you ready?" And the IO device will say yes, and then the computer will take that value. The output is similar, so the computer will ask, "Are you ready?" and then the output device will say yes, and then the computer will send the value to the IO port. Jump if. This will jump if a condition. This is one of the flags from the ALU that's the condition. The different jump if commands I can show you. So jump ifs. Here are all the conditions. So jump if positive, jump if 0, jump if carry, jump if negative, jump if even, jump if odd, jump if always. This always is basically just like always jump, so it's like an infinite loop. Jump if not 0, jump if not carry, jump if not overflow. So these are just like negated ones from like this. So you can jump if it's not 0 yet, or jump if it's not carry, stuff like that. Let me go back here. Reset. Okay. This is not one of the commands. I actually scrapped this because that would take too much wiring. If you want, I can add it in, but it'd be like cancerous to wire it up. Assign. This will basically take a value you specify and put into a register. I already showed move. For some reason, it's down here. Goodbye. And IO control, so that this will send a value to the IO control register. And by the way, there's no address we specify here, purposely because if you're using this, you have already used an out or an in command, which specifies a port address, and that address stays in the address register anyway. So it's fine. We don't need an address because the address is being already selected. I will show you the program. So, here's all the micro instructions for each command. This took me ages to make. Get all the way to the end. Okay, here's the demo program. So what we do is we take input from F. We take input from port 0, put that into F. Then we assign 1 to C. So we make the C register 1. We push C twice. So we get 2 copies of C in the stack. Then we output C. So because first number of Fibonacci is 1. Then we pop C off the register. No, we pop the top of the register, top of the stack off into register C. So this is just for, this might seem redundant, but this is for purposes when we're looping. And then we pop off the other C that was in the stack into D. So now the stack is empty, and we have, these are both the same now. Well, right now in this case, but usually they'd be different. Now we move C to A, we move D to B, so we can get ready to add them. We add, then we move that value into E, into the E register. So we move the value of C plus D into E. Then we output E. And we get a 2 out. So we went from a 1 to 2. So now we push C and we push E. So right now E is the top of the stack because we pushed that last. So right now it should be 2 and 1 in the stack. Then we move F to A. F, by the way, is the IO input thing. So if we specify like 5 numbers of Fibonacci, this is what that is. And then we assign B to be 0 because we don't want to be adding the previous B since we moved D to B. So now we want to decrement this because we already got one value of Fibonacci. And we move the output of that to F, and then we move F back to A. And we add. This add is just, it's not adding anything to F. It's keeping it the same because B is 0. I'm only doing this because this will actually it'll update the flags, which that's what it does. And once it updates the flags, then we can do a jump if because jump if uses flags conditions. And we jump if back to 8 if it is not 0. Because if it's 0, that means we've gotten to the end of our Fibonacci numbers. Otherwise, we jump back to 8. And 8 is here, where we pop C off. And remember, we're popping 2 and 1 off. So then this gets added, which is a 3. It gets outputted. Then we jump if back. We subtract 1 from the value. Now it's a 3 and a... It's a 3 and a 2 in C and D. We add those, we decrement, we go back. And right now it's a 5 outputted. Now we go to 8. Yeah, you see how this is going, basically. The stack is very useful in this case because we get to use it. So we don't have to have lots of move commands all over the place. We just need to be pushing and popping. So that's basically how it works. I will share a document to the TUNG Discord about it so everyone can look at it and see. And this is not a good computer by any means. It's like only my first, so I'll be making better ones sooner. I completely made it way too big, so yeah, I didn't use enough vertical space. See, like this is all underutilized, other than things on the walls. Okay, well, I guess I should start working on this display thing. I'm going to just look at this. Let's put it to 3. Let's put it to 5,000 so we can get to the end of Fibonacci quick. Because this is technically at the end. Okay, waiting for it. Okay, there. Now let's change it to... it's not truly amazing. I mean, many other people have done it already. Okay. Well, time to look at this in... Oof. Okay, well, thanks for looking, Jimmy. I'll see you next week. Actually, I'll probably be making a video about this whole computer, because I don't think everyone will see this stream. Right? Well, I'm not sure. Very dedicated viewers will see this stream. But I'll make a video about it, so it has some, like, good flow and everything, and well, I don't really rehearse for videos, but it'll be better than this stream anyway. Streams are convenient because I don't have to edit them. Okay. We're at 100 ticks per second. Okay, good. Oh yes, Jimmy, board stacking has been a problem. I have suffered. I don't know. I've just had to clone boards now and put them on one big board, which is not bad, but I have to do math to tell how big the board it should be. Okay, let's toggle halt. This should say something, maybe. Oof, my frames. Oh, wow. Great. I didn't even connect them up to the right ones this whole time. We must halt the computer and reset it. Oh yes. That ALU register is so broken. It just cannot be clocked. Well, it can't be like clocked in a short pulse. It's annoying. So this should really be this way. And hopefully this doesn't break it too, because I want this to look nice and stuff. Because right now it's just breaking the registers. Oh yes, it'd be interesting actually to see this. To see this working like this. Oh yeah, we're gonna be playing the sound card too, which will be interesting. Oof. That isn't reachable. Time to move this
Oh my
board.
gosh.
What?
For the amount of delay between 59 and 0, I need to put down 100 delayers.
Oh.
Yeah.
Make a board with like 10 delayers on it or something and then just clone
I
it.
think I have 50 right now, but I have to check. 2, 3, 4,
That is
5,
unfortunate.
6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20, 21, 22, 23, 26, 27, 8, 9, 30, 1, 2, 3, 4, 5, 6, 7, 8, 9, 40.
Oh yes, TUNG Tuesdays aren't over just because of the years. The school year is over.
50. Good. I have 50 inverters. Okay,
50
time to put boards up vertically.
vertical boards.
It is the only way.
A small price to pay for salvation.
It was the only way. Okay, 51.
There.
Darn.
Users 51?
No, it's fine.
Oh, okay, good.
Oh my gosh. Trying to connect it, it's like not being able to connect. 51, 2. Okay.
That should be fine in theory.
In theory.
Yeah. Only be 4 wires. Yeah, okay. That's fine, I think. 5,000 ticks it is. Actually, no, I think my computer can handle 6,000. Oh god, just nothing running is lagging the game. 5,500 ticks. Very laggy. 5,000 ticks. Why you lag? It was fine before. Okay, 3,000 is okay. Uh,
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 18 on this side. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. Wait, what? Okay,
What?
Okay. 18 plus 18, 36. I have 14 more, I think.
Oh.
If I math correctly. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 20, 1, 2. This is Cancer's wiring. 3, 4, 5, 6, 7,
Oh wow, I didn't wire this up
8,
correctly. Wow.
9, 30, 1,
It is doing it correctly at
2,
least. Yeah, it's adding and stuff. Okay, well,
3, 4,
Oh, I forgot I hooked up the
5,
sound card. Time for
6.
ear rape.
Why? Ear rape is my thing.
I just stopped the ear rape.
7, 8, 9. Okay. 40. Only 10 more to go. 1, 2, 3.
Okay, I'm
4,
just going to calculate like one Fibonacci
5,
number.
6.
Actually, no, just
1, 2, 3,
why is it lagging
4,
so much?
5, 6, 7, 8, 9, 50.
Oh no, this horrible thing.
Finally.
Oh, this glitch happens sometimes
What?
when the computer just like completely breaks and it just goes crazy. I think because of just bad timings on my part. There, now the computer theoretically is not broken. Hopefully it didn't erase anything in memory.
Ha.
It can't though, like I mean, it's very hard to erase something in memory. You have to like follow a very specific set of instructions, but it was just doing random
That's good.
It was just doing random stuff then, like it was just like completely broken. Control unit just completely broke, so no, it was the instruction register. The instruction register is really well, the timings are not good. So, yeah, it just breaks like that. Also, this is not hooked up correctly.
Yes. This is good. It works.
It works. Okay, good.
Okay, clone this thing.
This should work in theory too.
In theory.
Yeah. This is just this screen display is like an optical illusion, like all the wires connected up. It's crazy. Rail Javar's is much crazier though. Only one Fibonacci number. Because I want to do this quickly. Well, it's not really one Fibonacci number, it's just up to 2. Because, well, it's 0. It's counting Fibonacci numbers after 2. Really, that's what it is, because I don't know. I wasn't bothered to fix it, but it's okay. I guess you can somehow change the number of Fibonacci numbers there are.
This, in theory, should count minutes.
Minutes?
In theory. I'm going to 5 times the speed of regular seconds. And let's see. Just look at the lights in the back. They're like always on.
I can't see your
Oh yeah, I'm not screen sharing to save frames. There. Do the 2 ticks really matter?
2 ticks?
Yeah. Because in theory, in order for me to reset this from 59 to 60 to 0, I would need 1,000 delayers.
Oh.
So the 2 ticks don't really matter, right? The 2 ticks that these AND gates produce that will slow down the hours.
Yeah, I guess not.
Okay.
There's one person still watching.
That's probably me.
Okay, hello Corey, thanks for watching.
There is one dislike. That's probably from Jason.
Oh, it's probably from Dee Dee. I didn't
Oh,
run the
yeah, that
Discord.
also makes sense.
I want to start plotting something, come on.
Okay. It's fine if I leave these because deleting them would be hard. Right? This mess of delayers.
Yeah. If you want to decrease file size, you have to delete them though.
Oh, yeah. Okay, that's going to go into the clear function. Hopefully I do not delete something I'm not supposed to.
Okay, let me look here. Output F2.
Okay, there. I'm going to speed up the thing by 60 times.
Oh.
So that it should, in theory, do seconds instead of minutes. So it was 1,000, right?
The lag Corey though.
Okay, time to look at my Why? Okay, this does seconds instead of minutes, so it works.
Okay.
And now we need one for hours. Also, I have to change these because I can't do 100. That's like way too less of ticks per second.
Oh.
2,500. $3,000, 5,000. Sure.
So you have different clocks for different speeds?
Yeah, that's what I'm planning to do. Probably has to be higher because this is supposed to be milliseconds.
Oh, okay.
Okay, and then clone this board. Put it there. Every time reset happens, you add 1. Clear that.
So how many different binary counters do you have?
4.
4.
10 actually not 10, 20 milliseconds. Seconds, minutes, hours.
Cool.
I guess it can go up to 99 hours.
99 hours, yes.
After 99 hours, how do I make these stop?
After 99 hours?
I have to enable this, right? I mean disable this.
You have to disable that. That's like the source one, right?
Yeah.
Yeah, so you just have to disable that one.
Okay, I toggled place and ghost. Okay, so this is the inverter it has to go in.
Shouldn't you have 2 inverters?
I don't need an AND gate.
Oh yeah, because there's nothing else connected up to there anyway.
Yeah, I destroyed the inverter here because that's going to slow it down.
Oh, okay. If we mess up at graduation, Mr. Geiger is going to die us.
You shouldn't say that because that just reveals we're in 8th grade.
We already revealed you were in 8th grade a very long time ago on the stream.
You said everyone here is 14 and under.
Yeah.
Yeah,
The whole time
that
I
doesn't
was-
mean we're all
Jimmy
in
knows
8th
we're in
grade.
8th grade. Anyway.
Okay, let's see.
Hook up many BCD displays. Maybe
Yeah, I have to.
Yeah. Could you finish it today?
Probably not, it's 8:30.
When are you leaving?
Don't know. What is 99 again?
99, 64, 32, 2, and 1.
Okay. 64, 32, 2, 1. That is not needed. Okay, that should be 99. Okay, now once it reaches 99, we need to bring it around with mounts, obviously. And through pegs. Okay, in theory this should stop on 99. But in theory.
Okay. Let me look at this. We output this.
Actually, it shouldn't stop when it reaches 99, it should stop when it reaches 100.
Why? Why 100 hours?
Well, We can't make it stop right when it hits 99. We have to make it stop a bit before it reaches 100.
Yeah.
But that's way too hard, so we just make it stop when it hits 100.
Yeah, that's fine. Probably.
Well, that'll look weird, but it's fine.
It should count years.
Yes.
And centuries and decades.
I mean, right now it's running at 600,000 ticks per second. 60,000 ticks per second.
What the heck?
If we make it run at 1 tick per second, this could be counting pretty slow things. Like 10,000 hours. How long is that?
10,000 hours?
Yup.
How many years is that? Let me look.
I don't think that's 1 year.
Okay, yeah, probably not. 10,000.
Well, can we have decimal ticks per second?
That's 1.16 years.
Okay.
Can we get decimal second?
No, I got 1.14 years.
Oh.
Oh, okay. Well, can we have decimal ticks per second?
No, I tried putting decimal points.
Okay, that's okay. We have to move it all the way over here. Is that tall enough? Ha, yes. This goes all the way over there. Okay, in order to make this go at... I need to multiply this by 60 again, which makes it 3,600,000 ticks per second.
Wow.
Yeah, that was not a great idea. I don't want my game to run at 1 frame per second. So we're going to go with 600,000 ticks per second.
That's probably more reasonable.
That did not help.
Ooh. Yeah, Corey. That's not good. The game will lag like no matter what. I cannot run like 4,000. I cannot run
Okay,
like 6,000.
600,000 ticks is too much, so let's make it 200,000 ticks per second.
200,000.
That's much better.
That's much better. How is 200,000 ticks per second better? I can't even run 6,000 ticks per second without it lagging a lot.
Well, you have the computer.
Oh yeah.
I only have like 4 of these, except they're like real flashy. Okay, I need to wait for this to count to 99. Shoot, that's going to take a long time.
Well, this is
Okay,
great.
let's see if we can
Epilepsy
make it
warning.
300,000.
This is an epilepsy warning thing.
300,000 ticks per second makes it 20 frames per second. Yeah. No, now it's dropping. It's like...
It's making some interesting patterns.
Yes, that one. Oh, that one now. Oh, that one now. Oh, that one now. Is that random?
What's random?
The one thing that's on.
What one thing that's on?
That one pixel that's always on during the flashing that changes. Is that random?
Where?
Okay. Probably 10 seconds ago.
Or on which counter was it?
Not the counter, the screen.
Oh, it's just, yeah, because it's not changing because the program actually ended.
Is it random?
It isn't random, no. I'm trying to draw a line, but bad timing things are happening, so the whole screen goes crazy. But it actually, I'm pretty sure it did draw a line, but The screen's just doing bad things. You could see like the
I
picture.
guess I'll have to sit here for a while.
Why? You have to see it?
Yeah, I have to see if it stops at 100.
Ooh. Wait, how long do you have to wait?
Okay, let's calculate that. I'm running the game at 300,000 ticks per second.
And right
Normally
now,
1,000. That's 300 times the amount. 99 hours divided by 300.
99
Actually,
hours.
no, 100 hours. 1/3 of an hour, 20 minutes.
Okay, yeah, exactly.
Yeah,
Corey.
I don't have the time for that though.
Exactly. Corey, just hook up BCD displays to it and see if it works that way. It'd be...
Okay.
Yeah.
While that is going on, I'm going to hook up BCD's displays.
Yeah, it'll look nice then. And then you can have fun while you're waiting for 100.
Actually, I need to make a special 2-digit BCD display.
Yeah. For the hours, it's just 3-digit, basically, right?
Yeah, no.
Isn't
It's
hours...
also the 2. Yeah, I
hours
guess.
only goes up to 99?
Well, kind of. I'll just move this right now. Oh no, I cloned it. Okay, good. It's not as at a state where it breaks the game when it gets cloned and deleted.
I literally cannot clone my computer. It just dies. My computer dies.
Okay, I'm going to put that back there. Okay.
Okay, actually, let's not draw something to the screen. I want to place Megalovania on the sound card. That's a better idea.
That is a good idea.
Very good
I have to admit.
Yeah, okay. Let's delete the old program.
Okay, Double Dabble works with any number of bits, right?
Yes, any number.
Okay. Least significant is left. That means it's this one.
So it's starting at this memory address.
This is the amount of hours you've wasted playing Factorio.
You play Factorio?
No.
Oh. Factorio is a good game. It's very much like TUNG, like with circuitry almost.
I just rotated a wire.
Yeah, I know, you can rotate wires.
Yep.
It's amazing. Oh god, why?
Okay, 1, 2, 3, 4, 5. Where's the 6th one? This is the 6th one. This is the amount of years you've wasted playing Factorio.
I saw this video on Factorio of this guy making a ray tracing engine in Factorio. It was amazing. It was like a 3D. Well, it wasn't 3D, it was a ray tracer. It was like pseudo 3D, but it was amazing.
Okay, actually this is the amount. Whoa, it's at 39. Okay. That's the amount of hours you've wasted playing Factorio since today. Definitely. Okay.
Oh, yeah, 'cause
I have to make these up. Like, on top of this. Yes, I can make it on top of this.
Oh, yes.
2-digit 1, 2-digit 1, 2-digit. 3-digit, but the first digit, like, doesn't matter. So basically 2-digit. Let's see. Going to not yet. New board. There. Now I can clone this. Okay. The good thing is it doesn't break the game when it's cloned.
Oh, yes. Your BCD thing doesn't really crash the game.
The bad thing is I didn't place it correctly.
Ooh. You placed it on top of the layer, wow. I mean, on top of that thing there.
Okay, I have to move it left and wrong button. Wrong button again. Okay, now I have to find that. Move it back. Oh my gosh. Move it left. Oh my gosh.
I know, placing it on there is really annoying.
I need one of those scroll bars. I mean scroll wheels that can just scroll forever.
Oh yes, those.
Okay, there we go. I need to change this up though. Okay, through pegs. Most is this side, that would be most, so least is here.
What?
57 hours played. Okay, 57 hours wasted during Factorio so far.
Corey,
Yes.
you need to get a laptop for China. Yes, so you can do your stopwatch. And also we need to do TUNG Tuesday while you're in China. We have to carry on the tradition.
That's my mom. Yes. Yeah.
Oof.
OK。那就马上就回家。OK。
What?
OK。No. I can't give that. 马上 means around 50. Around 15 minutes later. Yup.
Corey, you need to finish your thing.
Okay. It's not Dayoshi.
It isn't playing, yeah.
没有Dayoshi.
Make your mom tune into the stream.
Yes. Yeah. because 需要你的电脑。Well, I started a project on his, and I can't move it over. Move it over well. Actually, I need to calculate I need right
Okay, how am I supposed to do this? Oof, the lag.
Yeah.
I'm just going to remember it like this.
I need to think of it. It's in theory I can. The thing I've been doing can finish in around 5 minutes. No, 自己走. Because I can't be done in 5 minutes. Okay, bye. You too. It'll be embarrassing because I'm still on stream. No. Okay, I love you, Mom. See you.
Oh yeah, let me actually hook up the control lines. It's
Hey, the moment of truth is coming, David. Actually, no, it's only at 81. David,
What?
I'm back.
Moment of truth time. I'm showing your screen on the screen.
It's 17 second. I mean, 17 times 1/5 minute longer. That's how much more time I need.
What about the milliseconds?
What?
Milliseconds and seconds, right?
Oh, I'm going to be doing that soon.
Okay.
Okay, we put a new board on here, which will be 1 by 2. Put it like that. V4, clone that. Oof. Okay, put it on top of that. Put it down like that. Okay, that's not good.
How much did I play of Megalovania?
Good amount.
A good amount. Okay, I guess so. For rests and stuff in the song, what I have to do is I have to leave white spaces in the memory. So like spaces where it's just 0. So then the computer just skips over it and doesn't do anything. That's what I have to do for rests and stuff.
Okay.
So I guess I'm doing this. Okay, for Megalovania, what we want to do is we want to output. Well, first, let's just say out, assign A to be 0. Actually, let's assign C, and then let's out C on port address 2. And then we can do IO control. I'm using IO control here because I don't have to specify a register since I already selected it. That's why I connected it up to the memory line. So IO control, let's just say IO. Now, the way I hooked it up, the first 4 bits are octave, and the second 4 bits are note. And they're from C to B. So,
Okay.
what's a good octave for Megalovania? I have to look.
Oh, my dad's calling. Hi.
Take off your headphones, it's ear rape.
Oh, we're at 9. Oh, David, we're at 97.
97?
Yeah,
It reaches
out of 100.
when it reaches 100 and it just doesn't work.
That would be horrible. It just skipped 99.
Ooh.
Ah, I see. I have this to make this toggle off. Ah. Big rip.
Okay, this is a good octave. Octave 4. So,
Ah. Okay. Least significant over here.
octave
Oh
4.
no,
So
it's lagging real bad. I have to change the tick rate to 60,000. That's 600,000. 60,000 there.
and then it's A. So dun dun dun. So A. What is it? Here's A. So 1010.
Yes.
What? You have to do it all over again?
No, look at this.
Yes. Very accurate. It doesn't even matter.
Actually, let's put it to 1,000, which is what it's supposed to be.
That should be every second.
Oh, I hooked it up to the wrong one. That makes sense.
Okay, yeah. I was going way too fast. That is A.
Okay, now time to painfully delete wires.
Deleting wires is painful. I can definitely say that.
Okay, least significant.
I'll just make it that octave, it's fine. And A. There. This is a good program. It'll play dun 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 dun. Everyone knows that's Megalovania at that point. So, let's just see if it works. Probably have to change the tick rate a lot. But it's fine. So this is 8 to the note first.
Okay, this is seconds. It's pretty close, I think. And I'm going to have to move the displays down and then rewire these things behind them. That thing behind it.
Yeah.
Yeah, that will be big rip.
We're going to get Megalovania working.
Are we?
Yes. Dun 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 dun. Okay, no.
Okay, that's not off by a lot. Good. Least significant. Actually, it should be over by 2. I mean by 1.
Oh wow, I'm stupid. I didn't even put in the program. Why did I expect that to run? Okay. Time to put in the very simple program. And
How simple is it?
it's 1, 2, 3, 4, 5. It's 7 lines.
Okay. Milliseconds is going crazy. Not milliseconds, 20 milliseconds is going crazy.
Wait, why didn't you just do milliseconds?
That was way too hard.
Oh.
Besides, it looks like 10 milliseconds. Milliseconds would have had to use a 1-tick clock, which wouldn't work. Right?
Yeah. Okay, yeah. Crazy.
It looks like 10 milliseconds, so it's good.
An Apple stopwatch is 1 millisecond, but yeah.
Okay, now I have to move these over in the best way possible.
Move the whole board, the computer dies.
No. Okay, what can I do here about this? I can put an inverter 3. Okay. 1, 2 ticks. 3 ticks. 4 ticks. 5 ticks. And then 2 delayers. David, would this clock be good?
How many ticks is it?
Shoot. Wait.
Yeah, that doesn't look right.
It's because this has to go into an inverter. There. Now it's right. Okay, would that be a constant rate?
I don't even see the light turning on.
It's turning on.
Oh, it's like not turning on and off.
It is.
Oh, I can't tell.
Well, would this be a constant pulse? I mean, not a not random pulse.
What do you clock it with?
This should be 25 ticks because it's 2,500.
I guess.
Okay, time to test. 2500. Let's look at the seconds. That seems a bit fast. No, that's right, that's good.
I have no compiler yet for my assembly language, so I have to like look up all the codes for every single instruction by myself, which is sad. Also, I don't have an input thing where you can't like write your program and then it inputs it line by line, like automatically, so you don't have to put it in. That'll be much better than this. Right now, this is just bad.
Okay, let's stop it. Okay, now 3,000 ticks per second.
Okay, well, time to copy all of these in.
Okay, that's 1, 2, 3, 4. Oh, come on. 4. 1, 2, 3, 4. 5. 6. 7. 8. 9. 10. That's 1. Put a delayer. That's 2. Hopefully that can reach. That reaches. And that's 3. Okay, good. It works.
Good.
Now let's do 5,000. With the exact same setup except with 4 inverters. Okay, can that reach? Yes, it can. Good. Okay, this works too. This looks good enough. I mean, it looks close enough to milliseconds. I mean, 10 milliseconds. You don't have to know it's 20 milliseconds.
Oh.
Okay, that can go here.
Rip. We're gonna have to wire that up, Corey.
No, I'm leaving. You wire this up.
No.
Just kidding.
Okay. I have time
Okay,
left.
this is 6-bit, right?
Yeah.
But
Looks like
this is 7-bit. Okay, this one will be a bit different than these. Okay, let's see. 1, 2, 3, 4, 5, 6. Why is my voice so loud?
I turned up the volume.
Why?
So
Okay,
I need to hear. I need to hear the sound cards.
4, 8, 9, 19. Should be 19 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4. 19 by 14. Okay. One, two, three, four, 1. Hi. Oh, yeah. Oh, okay, I have to leave and get in 2 minutes.
In 2
Oh.
minutes?
I have to leave and get home in 2 minutes.
Oh. Oof.
Okay, I will save this board as stop. Oh, wait, caps lock. Stop watch. 1. Not done. Corey.
D, what are you doing? Stop ear raping people. Stop.
Okay, if you want to play with the stopwatch,
Stop, Dee.
it's not even loud.
Do you push it?
Yup.
Okay. So you're gonna leave?
Yup.
Oof. Corey has left. All in the stream now, I guess. Okay, well, goodbye, guys. My non-existent viewers. Okay, goodbye, everyone.
Dude, you have 42 subscribers. You're getting some subscribers. Just chop your head off.
What?
Give me some subscribers.
I can't.
Give me some subscribers.
Why do you want subscribers?
Because I only have 7.
Okay.
How long have you had your YouTube channel?
Maybe a couple years now, but I was inactive for like a year, so it doesn't matter.
Well, guess what? I've been starting. I've had it for like less than like 3 months, and I already have 7 subscribers.
7 subscribers in 3 months. Never done before.
Yes. It's because everyone either gets like a million subs.
Okay, bye, guys. See you next week, next TUNG Tuesday. Bye.